Hello everyone, I am Mete Ahunbay, and today I will be talking about the price of Anarchy of two-buyer sequential multi-unit auctions, with complete information. This is joint work with Adrian Vetta. We consider sequential auctions in which identical copies of an item are sold one by one in a sequence of individual second or first price auctions. As the title of the presentation indicates, we work in the complete information setting, where there are two buyers. Sequential multi-unit auctions have widespread practical applications, for example, wine auctions and livestock auctions, but the form of their equilibria and efficiency is still not fully understood. One characteristic property of these auctions is the declining price anomaly. Prices tend to weakly decline in real examples of such auctions. First noted by Ashenfelter, this phenomenon has been empirically confirmed numerous times. To explain this anomaly, Gale and Stegeman introduced the two-buyer and complete information model we use and proved that the unique equilibrium that survives the elimination of dominated strategies in fact exhibits declining prices. Therefore, the declining price anomaly is in fact natural equilibrium behavior in this setting. Bea L, in this setting, showed that the price of Anarchy is exactly 1 minus 1 over E if the buyers also have decreasing marginal valuations. Unfortunately, though, their proof contained errors. Rodriguez managed to show that the declining price anomaly also holds an undominated equilibrium in the complete information setting, even for arbitrarily many buyers, by linking equilibria to a natural behavioral strategy buyers may employ. However, his result depends on very strong symmetry and concavity assumption on buyers' valuations, lacking full generality. Later, a work of Paislemea et al., amongst other results, extended the equilibrium concept of Gale and Stegeman to arbitrarily many buyers. Prevey et al. Showed that the declining price anomaly need not hold for such equilibria of sequential multi-unit auctions, but showed empirical evidence that counterexamples may be rare. Finally, in recent work, joint with Brendan Lucier, we showed that in the two-buyer and complete information setting, if we also assume that buyers have concave valuations and that they do not bid above their valuation for another item at each individual auction, then the results of Gale and Stegeman, Rodriguez, and Bea et al. Still hold. Prices decline through the equilibrium. Equilibrium bids are intrinsically linked to a natural behavioral strategy, and the price of Anarchy is exactly 1 minus 1 over E. However, it is worth noting that overbidding can arise naturally in undominated strategies, even in the two-buyer setting where there is no signaling behavior in equilibrium. In our work, we restore the price of Anarchy result of Bea et al. In the two-buyer and complete information setting, i.e. when we do not make an overbidding assumption. Now, there's a vast literature on the efficiency of auctions. But sequentiality in auctions is generally problematic. The temporal nature of such auctions implies large extended representations, which makes analysis difficult. In fact, positive results on efficiency are often proved under a unit demandness assumption, while more general valuations are shown to have vanishing efficiency due to emergent signaling behavior. Sequential multi-unit auctions are actually special in this regard. The results up so far instead hint at a 1 minus 1 over E price of Anarchy, even for arbitrarily many buyers. To deal with sequentiality, we could attempt to deduce the form of equilibrium, like in Rodriguez's or in our recent work. Sadly, without the no overbidding assumption, such a behavioral characterization is not possible. To deal with sequentiality, we will instead reduce the problem of worst-case efficiency to a class of minimization programs. Closed-form solutions for these programs will then allow us to obtain tight price of Anarchy bounds. We will show that for non-decreasing and concave valuations, the price of Anarchy is exactly 1 minus 1 over E. Without the concavity assumption, we will show that the worst-case efficiency of a T-item sequential multi-unit auction with two buyers is exactly 1 over T. Now, let's take a look at our auction model. There are two buyers and T items for sale. We assume that each buyer has a non-decreasing valuation function for the items they obtain. We will opt to represent this function by its marginals. The incremental valuation Vik denotes buyer i's valuation for a kth additional item. Note that if buyers' valuations are non-decreasing, then incremental valuations are non-negative. Likewise, if buyers' valuations are concave, then incremental valuations are weakly decreasing. We can represent incremental valuations graphically. For example, suppose 3 items are for sale, and buyer 1 has value 6 for her first item, 4 for her second item, and 3 for her third item. Then buyer 1's incremental valuations can be represented as in the diagram, displayed histogrammatically from left to right. Likewise, if buyer 2 has value 4 for his first item, 3 for his second item, and 0 for his third item, then buyer 2's incremental valuations can be represented as in the diagram, displayed this time from right to left. In this presentation, we will opt to combine these diagrams into one. By convention, the blue line left to right will display incremental valuations of buyer 1, while the red line right to left will display the incremental valuations of buyer 2. Now, with 2 buyers present, in the unique equilibrium surviving the deletion of dominated strategies, buyers will condition their bids on the number of items currently allocated to each buyer. So, the set of interim and final allocation of items forms all relevant states of auction as far as the bidding strategies and outcomes are concerned. Call X a decision node if X corresponds to an interim allocation. We can then assign a forward utility UIX, denoting the utility buyer I has in the sub-auction starting onwards from decision node X. Instead, if X is a final allocation, note that the auction has ended, so we let UIX equal 0 instead. When X is a decision node, the forward utility is simple to compute through backwards induction, given the bids. If buyer I wins at X, then his forward utility at X is his valuation for the item he wins, plus his forward utility in the rest of the auction, minus the other buyer's bid. If buyer I loses at X, his utility is then exactly his utility in the rest of the auction. But how do buyers bid? There is in fact a unique equilibrium bidding strategy which survives the iterative elimination of weakly dominated strategies, which equals a buyer's value for winning minus the buyer's value for losing. This is equal to a buyer's incremental valuation for the item being sold, plus the utility in the rest of the auction if they win, minus the utility in the rest of the auction if they lose. With these bidding strategies, buyers are indifferent to tie-breaking, and in fact their utility is given by a simple expression, denoting by capital UX the sum of buyers' forward utilities. Each buyer's forward utility is then as shown. The evolution of the auction can be represented graphically. Here is a small example when buyer 1 has value 10 for each item she wins, while buyer 2 has value 5 for his first item and 0 for his second item. Each node is labeled by a table. The top row corresponds to the allocation corresponding to the node. For example, the beginning of the auction is labeled 0, 0. The bottom row, in turn, displays buyer's utilities. At decision node 0, 0, buyer 1 has utility 10, and buyer 2 has utility 0. Left arcs point from decision node X to a decision node corresponding to buyer 1 winning. For example, the left arc from 0, 0 points to 1, 0. Right arcs likewise correspond to buyer 2 winning. Each arc is labeled by the corresponding buyer's bid at its source node. An arc is solid if it's labeled by a winning bid, and a realization of the equilibrium path is bolded. A quick note on the graphical representation. In this talk, we will only be concerned with possible equilibrium paths. In this case, we will remove all labels and all non-solid arcs, leaving a simple diagram showing which buyer can win at which decision node. Let us now discuss welfare and efficiency. Our definition of welfare is standard. The social welfare for the allocation where buyer 1 wins k items is given by buyer 1's valuation for k items plus buyer 2's valuation for the remaining t minus k items. This notion of social welfare can be extended, of course, to the social welfare at any sub-auction starting from a given decision node X. The optimum social welfare at decision node X is then the maximum social welfare amongst allocations reachable from X onwards. And if P is a path from decision node X on which buyer 1 wins k items, and if the optimum social welfare at X is not 0, then the efficiency of P is the ratio of the optimum social welfare and the social welfare at X when buyer 1 wins k items. We are concerned with the price of anarchy. So how can we represent it? Of course, the price of anarchy is the infimum of possible efficiencies of any equilibrium path for any number t of items up for sale and for any valuations of buyers 1 and 2. The efficiency of the equilibrium path depends on k, the number of items allocated to buyer 1. We want buyers' valuations to be non-decreasing, so incremental valuations should be non-negative. Furthermore, V1 and V2 should be that in equilibrium, there's an equilibrium path to the final allocation k, t minus k. Now, we can scale all valuations, utilities, and bids by a constant and get another auction with the same efficiency. Therefore, we can normalize the optimal social welfare to 1, adding it to the set of constraints and removing it from the denominator of the objective. Furthermore, by previously shown arguments, the efficiency of an auction is greater than that of a sub-auction in which it is optimal for one buyer to win all items. Since the infimum runs over all t, without loss of generality, we can assume that it is optimal for buyer 1 to obtain all items. By our normalization, it means that social welfare equals 1 if buyer 1 is allocated all items and is less than or equal to 1 otherwise. Finally, note that the social welfare terms are all linear in buyer's incremental valuations. Fixing t and k and substituting in the social welfare terms, we then obtain a conditional minimization program. This program is almost an LP. The objective is linear, but the feasible region is unknown. The feasible region is in fact a union of polytopes, as can be shown by a construction of this program with quadratic constraints. The nonlinearity then arises from the equilibrium path existence constraint. To handle these constraints, we will seek inequalities that are valid when there exists an equilibrium path from the beginning of the auction to final allocation k, t minus k, and substitute those inequalities for the path existence constraint. So, the question is, what do these inequalities look like? Our valid inequalities have the following form. But what do these inequalities mean, really? Well, it turns out that they describe buyer 2's payoff for purchasing t minus k items in another setting. To see this, suppose that buyer 2 has to pay for his ith item the following quantity. Buyer 1 would actually make these bids at decision node 0, i minus 1 under a certain condition. To deduce this condition, let us compare p star I and buyer 1's bid at 0, i minus 1. Comparing the terms, it is evident that buyer 1 should believe 1. That she can purchase her k items each at price 0 on the equilibrium path after buyer 2 wins the current item up for sale, and 2. If buyer 1 instead purchases an item, she purchases the remaining items at buyer 2's current incremental valuation. These beliefs are sometimes true, but not always. For example, they certainly hold when equilibrium paths look like this, and buyer 2's incremental valuation for his t minus k plus 1 item equals 0. However, these assumptions may not hold in general. Going back, suppose that buyer 2 is asked to purchase up to t minus k items, where he needs to price p star I for his ith item. The valid inequalities then tell us that buyer 2 should purchase all t minus k items. To show this diagrammatically, suppose that there are 6 items up for sale, that buyer 1 has value 1 for each item she obtains, and that buyer 1 obtains 2 items in equilibrium. We mark by the purple dashed line possible valuations for buyer 2, which would set p star I equal to buyer 2's ith incremental valuation. Of course, buyer 2 can have valuations higher or lower than this purple dashed line. Then we mark by the golden dotted line p star I. Note that when buyer 2's valuation for an item is higher than the purple dashed line, his price for the item is lower, and vice versa. Let us then mark buyer 2's payoff for each item he purchases. If an area is shaded green, then buyer 2 obtains the item for a price lower than his valuation, and if the area is shaded red, buyer 2 overpays for the item. The valid inequalities then say these forward sums are all greater than or equal to 0, meaning buyer 2 would like to keep purchasing up to t minus k items when offered these prices. How do we prove these inequalities are valid, though? To derive our valid inequalities, we in fact prove an upper bound on buyer 2's utilities. It is worth noting how the proof actually exploits the two-dimensional nature of the game tree. So, suppose that buyer 2 wins at the beginning of the equilibrium path. Take the game tree, where x is the topmost decision node, and focus only on the nodes of the game tree. We will want to track our algebraic manipulations on this diagram. To do so, we will represent expressions involving utilities by labeling each node with an ordered pair. The first element of the pair will show the sign of the coefficient of the corresponding U1 term, while the second element will show the sign of the corresponding U2 term. Then the sum of U2s we have can be represented with the following diagram. Now, as buyer 2 wins at decision node x, U2x equals buyer 2's incremental valuation plus his utility in the rest of the auction minus buyer 1's bid. Substituting in for U2x, the label at x disappears. The decision node corresponding to buyer 2's win gains a label plus plus, while the label of the node corresponding to buyer 1's win becomes a minus plus due to the U1 term. However, the terms corresponding to the minus plus label correspond to this expression here. The max term for the utilities have cancelled each other, leaving only utility and incremental valuation terms. Substituting in, we push a new 0 plus label at x plus 1, 1, while converting the label of x plus 2e1 to a minus plus. Iterating on such equalities, we push the plane of 0 pluses down in the direction corresponding to buyer 2 winning. We have a minus plus label for the node at the lower left corner, but that's a terminal node, so utilities there equal 0, so we can throw out those terms. This iterative process then leaves us with a sum of U2s on which we can use an induction hypothesis, plus buyer 1's utility in the rest of the auction, plus some incremental valuation terms. Since prices are decreasing and valuations are non-negative, buyer 1's forward utility here is upper bounded by her valuation for the remaining items she will win. Then these terms all combined yield the inequality we deserve. These valid inequalities provide tight conditional efficiency bounds. In a T-round 2-buyer sequential multi-unit auction, if valuations are concave and non-decreasing, if buyer 1 is given all items in an optimal welfare allocation, and if there's an equilibrium path to final allocation kt minus k, then the conditional worst case efficiency equals this simple expression here. If the concavity assumption is dropped, the worst case social welfare equals 1 over t instead. For the proof, we replace the equilibrium existence constraint with the valid inequalities we obtained. For concave valuation functions, we also add in the constraint that incremental valuations are non-increasing. We then consider the dual linear program. Here, sigma terms correspond to social welfare constraints, kappa terms correspond to concavity constraints, and mu terms correspond to our valid inequalities. And this dual LP does have a solution with the desired value. On the other hand, we can show a valuation profile which matches this lower bound. In the diagram, we show an example when there are 12 items for sale and buyer 1 obtains 5 items in equilibrium. It is worth noting that this is exactly the form of worst-case valuation profiles proposed by Bea et. And if you look at our dual solution in our paper, these valuations profiles are actually obtainable from complementary slackness. Without the concavity restriction, we have basically the same LP, without the concavity constraints, of course. The dual LP then has the following form, without the terms corresponding to concavity constraints. This dual program has a simple solution of value 1 over t. We simply set sigma t and mu 0 equal to 1 over t and all other variables 0. And again, there's a valuation profile which has 1 over t efficiency obtained by complementary slackness. We let buyer 1 have value 1 for her t item and 0 otherwise. We let buyer 2 have value 1 over t for his first item and 0 for each additional item he obtains. Then the optimum welfare equals 1, and any allocation which gives an item to buyer 2 has efficiency 1 over t. Furthermore, for each k less than t, there's an equilibrium path which allocates k items to buyer 1. These simple closed-form conditional worst-case efficiencies then provide us with tight price of anarchy bounds. In particular, when valuations are concave and non-decreasing, the price of anarchy is exactly 1 minus 1 over e. Providing the asymptotic bound is straightforward. For any t and k, the conditional worst-case efficiency is bounded below by 1 minus 1 over e. However, as t goes to infinity, the worst-case efficiency when buyer 1 obtains a 1 over e fraction of items actually converges to 1 minus 1 over e. How can we move on from here? Well, the form of equilibrium, the form of the price trajectory, and the price of anarchy are all still unknown for sequential multi-unit auctions with or without overbidding allowed. Also, positive or negative efficiency results for two buyers and more general valuations functions remain to be shown. As we noted, our technique is very specialized to two buyers and identical items, since it depends on the two-dimensionality of the game tree. As a result, it is not directly applicable to any of the above settings. Still, it may be possible to modify our techniques to extend our results. Well, that is all. Thank you all very much for listening.